Okay, for what we're going to be looking into, we're going to make the transition from the real number system to the complex number system. And now, different books can use different letters, but for complex numbers, okay, the dominant one is the letter I. And now in the real number system, real numbers do not allow for the square roots of or even roots of negative numbers. Now we have for the complex numbers, okay, there is an allowance. And now for the letter I, this is going to be in reference to the square root of -1. And if I square out I goes to I squared, and the square of the square root of -1 goes to -1. And just a bit of a sampling of reducing complex numbers in terms of the letter I. Let's say that if you have the square root of the negative of a perfect square, like in the case of the square root of -16, and if I look at taking what we have here, okay, so I can say that I have the square root of 16 times the square root of -1. Square root of 16 is going to be at 4. And once again, we have square root of -1 is in reference to I. So we have for the square root of -16, that is going to end up at 4i. And let's say that if I have another opposite sign of a perfect square number with -100, and if I reduce in terms of the letter I, so I had the square root of -100 is a complex number, and putting in terms of the variable I, square root of 100 is at 10, square root of -1 is at I, so the square root of -100 is at 10i. Now, for the square root of -27, 27 is not a perfect square number, but it is nonetheless a value that can be reduced in the square root. And for the square root of 27, that is reducible to the square root of 9 times the square root of 3. And the square root of -1 becomes I. And as a reduced radical, we can say we have 3 times the square root of 3 times I. And since I does not go inside the radical, you could also write this, and to safeguard I from seeming to appear to go underneath the radical, only the square root of 3, we can write this as 3i times the square root of 3. Now another number that, like 27, is the multiple of a perfect square, even though it is not a perfect square in its own right, we have in the case of 98, now we have the square root of -98. And if we factor out gradually, okay, we have the square root of 98 times the square root of -1. Now, in terms of reduction, now the highest perfect square divisible into 98 is going to be 49. So we have square root of 49 times the square root of 2. And we have with the square root of -1, that goes to I. And in terms of the reduction, we can say, in effect, that we have 7 times the square root of 2 times I. And you can also put the I out in front of the radical, so we can say we have 7i times the square root of 2. Now, for the square root of -63, we can say we have square root of 63 times the square root of -1. And like 27 and 98, 63 can be reduced. And so we have with 63, highest perfect square that is divisible into 63 is going to be at 9. And so we can say we have 3 times the square root of 7 times I, or 3i times the square root of 7. Now, let's say that for what we have in the case of complex numbers, if we're looking at interacting, and there is a rule of thumb, okay, whenever you're interacting with complex numbers, okay, now when multiplying or dividing complex numbers, okay, you want to go ahead and factor out the I first. I'll give you just some quick instances here. And let's say that if we have the multiplication, and we'll say that we have the square root of -9 times, the square root of -4. Now, what you're going to do here is that you're not going to take the square root of -9 times -4. Again, you're going to factor out I first of all. So for what we have in the setup, we have for the square root of -9, we can say we have square root of 9 times I. For the square root of -4, I have the square root of 4 times I. Square root of 9I, this will go to 3I. Square root of 4I, this will go to 2I. 3 times 2 is 6. I times I becomes I squared. And guess what? Going back, we have with I squared, that is equal to -1. So we have 6 times -1. And so for the product of the square root of -9 and the square root of -4, this will go to -6. And let's say that if we have, as another case, if I have the square root of -10 times the square root of -5. So I can factor out the letter I. Square root of -10, that's the square root of 10I. Square root of -5, okay, that will be the square root of 5 times I. And multiplying together, we have the square root of 50, I squared. Square root of 50. 50 is not a perfect square, but this can be reduced. I squared goes to -1. And we have square root of 25 is 5 times the square root of 2. Then we have times -1. And so for what we have in effect, multiplying everything together, so we're going to end up with the output. This will be the negative of 5 times the square root of 2. And we have as yet another instance. Okay, and we'll cross over to the operation of division. And let's say that if we had the square root of -80 divided by the square root of 5. Again, in the case of working with complex numbers, whether you're working with multiplication or division, go ahead and factor out the I first. So we had the square root of -80, so this would be the square root of 80 times I. We have over the square root of 5. And for the square root of 80, highest perfect square that is divisible into 80 is going to be 16. So we can say we have the square root of 16 times the square root of 5 times I. And we have all over the square root of 5. And here we can have square roots of 5 to cancel out. And for what we have in this particular instance, square root of 16 is 4. And we have times I. And so that is going to be the reduction in this particular regard. Okay. And now, just case here that we have regarding complex numbers, and we have here, again, just laying the foundation. Once again, we have I is equal to the square root of -1. I squared is equal to -1. And we have with complex numbers. Now, the standard form of a complex number is going to be A plus BI. And let's say that if we have writing in terms of the standard form, and we have, let's say, if we take as examples here, and let's say that we write in standard form, or in this case, a plus bi form. And we'll say that we have in our operations, we'll say the first case, we'll say we have 3 plus the square root of -4, and we have plus the square root of 5 minus the square root of -64. Okay, so we have complex numbers in the mix. And let's say that if I go ahead and translate out the square roots of -4 and -64, so we have in the rewrite, we're going to have 3 plus 2i quantity. And for 5 minus the square root of -64, we have 5 minus 8i. And removing the parentheses, we have 3 plus 2i plus 5 minus 8i. And combining the real coefficients, so we have 3 plus 5 plus, in the complex numbers, we have 2i minus 8i. So we have altogether 3 plus 5 is 8. 2i minus 8i, this will become -6i. So we have 8 minus 6i. Now, and let's say that if we have multiplying complex numbers together, and we'll say that we have the square root of 5 plus the square root of 7i, and we have times the quantity of the square root of 5 minus the square root of 7 times I. So if we look at multiplying together, now we'll do this one gradually. So we have the square root of 5 times itself, that is going to be the first product, and we have with the outside products, okay, so you have square root of 5 times the negative of the square root of 7 times I, and then we have for the inside product, we have the square root of 7i times the square root of 5, and for what we have in the case of the last of the products, okay, so we have the square root of 7 I times the negative of the square root of 7 times I. So we have with the first product, okay, this is going to be reducible, so we have the square root of 25, and then we have the negative of the square root of 35 times I. Next product, we have square root of 7 times the square root of 5, that would be square root of 35, and we have I attached, and then we have positive times the negative is a negative, and we have square root of 49 I squared. Now we have with the I terms of first degree in the middle, okay, so these will cancel out, and we have for the square root of 25 that goes to 5. We have on the far right, square root of 49 is 7. I squared is going to be at -1. So you have 5 minus -7, and of course, negative times the negative is going to be a positive. So we have for the end result here, we have 5 plus 7 to end up at 12. Okay, so we have in the end result, okay, you have 12. And that could also be written, if we're putting in a plus bi form, you can see we have 12 plus 0i. Okay, going back to complex numbers, again, we just looked at the standard form of a complex number, okay, is a plus bi. Okay, going back to what we have with complex numbers, we had The standard form of a complex number is a plus bi, and now we're going to be looking into complex conjugates, but let me give you a case where if you're looking at expressing in terms of a plus bi, and we'll say that we have, let's say we have the square of a complex number that is in standard form. Say if we have 4 plus 3i quantity squared, and in this one, okay, so for the square of 4 plus 3i, okay, so that's going to be 4 plus 3i times itself. And taking what we have now, applying the FOIL method, okay, so you have 4 times 4 is 16. Outside product we have 4 times 3i, which will be 12i. Inside product is going to be 3i times 4, which will be 12i. 3i times 3i, okay, we have at 9i squared. And in terms of following through, we have 16. 12i plus 12i is going to be 24i. 9i squared is going to be 9 times negative 1. So we have 16 plus 24i. 9 times negative 1 is negative 9. And combining like terms together, we have the product to result as a standard form complex number where we end up at 7 plus 24i. Now, in the crossover to what we have regarding complex conjugates, and what's going to happen here is that with complex conjugates, okay, it's going to have a feel of taking the factorization of differences of squares. And now, for complex conjugates, okay, now we're going to have the conjugate of a plus bi is going to be a minus bi, and vice versa. And we'll just take as samples of conjugates in a moment. Rule of thumb here. The product of conjugates is a constant. And let's say that if we're looking at identifying conjugates of given numbers, so in taking what we have here, I'm saying the lead off, okay, say if we have complex number at 4 plus 3i, okay, now again, conjugate of a plus bi is a minus bi, and vice versa, so we have 4 plus 3i, so a is represented by 4, bi is represented by 3i, and we have for the layout in this one, the conjugate is going to be at 4 minus 3i. And let's say that for what we have in the case of second item, if we have negative 3 minus 6i, and the conjugate is going to be negative 3 plus 6i. And if we have, let's say for third case, all right, so we have for 17, okay, the conjugate is going to be 17, and that could also be written as 17 plus 0i, or 17 minus 0i. They still both end up at 17. And let's say that if we have So you have a number, say we have negative 14i, and the conjugate is going to be positive 14i. And if you had to explicitly give the a in the a plus bi form, you have 0 plus 14i. And let's say that for conjugates, another thing about conjugates, convert fractions to standard form, or the use of conjugates can be used to convert fractions to standard form. And let's say that, okay, and what I mean by standard, I'm talking about a plus bi form. Okay, and let's say that if you have, as the case here, so you have a fraction such as 3 over 2i, and what you're going to do here is that you're going to take the conjugate of 2i, the denominator, and you're going to multiply the ratio by 1 in the form of the conjugate divided by itself. And for what we have here, we have 3 times negative 2i. It's going to be negative 6i. 2 times negative 2 is negative 4. Now we have I squared. So we still have negative 6i, negative 4i squared. So we have negative 4 times negative 1. So we have negative 6i over 4. So that is going to become negative 3 halves I. And just really contingent upon how Alex accepts some of these answers, this could also be written as 0 minus 3 halves of I. And let's say that if we have another case of reduction, and we will say that we have, as a case here, we'll go with 4 plus 3i all over 3 minus I. So again, I'm going to rewrite this taking the conjugate of the denominator. So I have here, so I got 4 plus 3i over 3 minus I, and for the conjugate of the denominator, that's going to be 3 plus I, and I'm going to multiply this ratio by 1 in the form of 3 plus I over 3 plus I. If I distribute, okay, so you have, in this instance, okay, so we got 4 times 3 is 12, and we have plus 4i, 3i times 3, okay, so this will become 9i, and then we have plus 3i squared. And for what we have in the denominator, we have 3 times 3 is 9, we have plus 3i minus 3i, we have minus I squared, we have additive inverses in the denominator, okay, that will go out. Now combining what we have here, okay, so you have 12, 4i plus 9i is 13i, 3i squared, so that's going to be 3 times negative 1. And we have 9 minus I squared, so you have 9 minus negative 1. Now we'll just move down here, so you have 12 plus 13i minus 3. 9 minus negative 1 becomes 10. And and we have 12 minus 3 is 9, plus 13i over 10. Now, in a lot of situations, okay, this would be a final answer, but if I'm looking at it explicitly in terms of standard form, I'm going to break up this expression into distinct radical terms. So we're going to have, for a, I'm going to have 9/10, and for representation of bi, that's going to be plus 13/10 of I.